Hey guys, welcome back to Joanne's Learning Hub. In today's video, we would be learning about stoichiometry in IGCSE Chemistry. Now this is a really important topic and there's always a question about it in the paper. So before I begin, I would like to thank Science with Hazel. Her videos have been a great help throughout my IGCSE preparation, especially the table method for stoichiometry calculations, and that's what I would be using in this video as well. So do check out her videos, and I've mentioned the link to her channel in the description box below. So let's get started. First up is the formulae of compounds. Now we know that every element has its own chemical symbol. Sodium has Na, carbon is C, oxygen is O. You must also know that there are something called compound ions. So these are ions made up of a group of different atoms which are covalently bonded together and have an overall charge. For example, the nitrate ion has the charge NO3-, so that's how it's written. And that's a compound ion. Carbonate is CO3-2-, and so on. So now you must know the definition of a molecular formula. The molecular formula of a compound shows the number of different types of atoms in one molecule. And some examples of formulae which would be important is carbon dioxide, which is CO2, NH3, which is ammonia, H2O, water, sodium chloride, NaCl, carbon monoxide is CO, CuSO4, copper sulfate, SO2 is sulfur dioxide, hydrochloric acid is HCl, and sulfuric acid is H2SO4. Now this is a method of how we work out the formulae of common compounds, so it's more like cross multiplication. If we take the example of aluminium oxide, now aluminium, it's in group 3, so it loses 3 electrons to form Al3+ ion. Oxide, it's basically oxygen and it's in group 6, so it gains 2 electrons to complete its octet. That's why it becomes O2- ion. Now if you cross multiply or swap the places of these ions, it becomes Al2O3, and we will not take into account the sign. So there won't be any minus, it's just plus. So Al2O3, and that is the formula of aluminium oxide. Now if we take magnesium nitrate, magnesium, it's a group 2 metal, Mg2+. Nitrate is an ion, it's a compound ion, so NO3-. And now Mg2+, so the 2 will move to the nitrate ion, whereas the minus, which is basically -1, will move to the magnesium. So it becomes Mg, then NO3. Now the 3 will not be touched. So you'll just enclose the nitrate ion in bracket and put a hole twice outside it. So it becomes MgNO3 whole twice. These are the formulae of some compound ions which would be helpful if you remember. Hydrogen is H+, that's not a compound ion. We have ammonium ion, this is NH4+. Do not get confused between ammonium ion and ammonia. Ammonia is NH3, whereas ammonium ion is NH4+. Hydroxide ion is OH-, oxide ion is O2-, sulfate ion is SO4-2-, sulfide ion is S2-, carbonate ion is CO3-2-, hydrogen carbonate ion is HCO3-, and nitrate ion, we've used this in the example, it's NO3-. Now let's discuss how we balance equations. Now a chemical reaction is the process of going from the reactants, which are usually on the left side, to the products. And we can show this chemical reaction either by writing word equations or by writing symbol equations. When you balance equations, you must remember that you can put numbers only in front of the formulas when needed, which means you can put the number here, 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 or here, but you cannot change these numbers right here. So this is an example of an unbalanced equation. H2SO4 plus NaOH, which gives Na2SO4 plus H2O. So the process of balancing this equation, first draw a dotted line and write all the elements on both sides. They are the same. So we have hydrogen, sulfur, oxygen and sodium. Count the number of hydrogen which is there on both the left side and the right side. Now for the left side there are 2 plus 1 which is 3 hydrogen. On the right side there is just 2 hydrogens. Sulfur, there is 1 on both sides, so 1, 1. Oxygen, there is 4 plus 1 which is 5 on the left side and 4 plus 1 which is 5 on the right side. Sodium, there is just 1 on the left side but there is 2 on the right side. So now from these numbers we can see that sodium and oxygen, the numbers are equal, but hydrogen and sulfur and oxygen are balanced, but the hydrogen and sodium require balancing. So if we make sodium equal, so we multiply this by 2 just to make it 2, so 2 and 2, and add a big 2 over here. We'll get 2 sodiums, now 2 here, 2 here, 2 oxygen plus 4, so that makes it 6. This will become 6. And if we have to add a big 2 here as well, because hydrogen now becomes 2 plus 2 which is 4. 4 hydrogen this side, and if we add 2 2s are 4, so this becomes 4 on this side as well. So hydrogens are balanced on both sides. Sulfur is already balanced. Oxygen, again 2 oxygen plus 4. 2 plus 4 is 6. This becomes 6, again balanced. And our sodium is 2 and 2 on both sides. So all the 4 elements have now become balanced. So this is how we make our chemical equation balanced. Now when balancing equations, you have to include state symbols as well. So these tell you the state of a substance in an equation. We have 4 state symbols: S for solid, L for liquid, G for gas, and AQ stands for aqueous. And aqueous means dissolved in water. Now you may be asked to write ionic equations as well. What are these ionic equations? These are equations that show the useful bit of reactions. So to write an ionic equation, you need to look at the balance symbol equation. Take out and cancel any aqueous dissolved ions that are present on both sides of the equation. So you'll only look out for the aqueous ions. Now in this example right here, CaCl2, this is aqueous, plus 2NaOH, again it's aqueous, gives CaOH whole twice, this is solid, plus 2NaCl, which is again aqueous. Your first step which you need to do is write out the ions. So Ca2 plus 2Cl minus ion plus 2Na2OH minus. You will not change the solid compound. So now CaOH whole twice, since it's solid, it's not aqueous, so you're not going to break it down into ions. And then we have again 2Na plus and 2Cl minus. Now we begin cancelling. We have 2Cl minus on this side and 2Cl minus on this side. 2Na plus on this side, 2Na plus on this side. So since we haven't broken down CaOH whole twice into Ca2 plus and 2OH minus, the final ionic equation will be Ca2 plus 2OH minus gives CaOH whole twice. And remember to include the state symbols. So Ca2 plus, this is aqueous. This 2OH minus is also aqueous. Whereas CaOH whole twice is solid. You can just put down the state symbols in brackets. Now for some definitions. Relative atomic mass and relative molecular mass. Relative atomic mass, it's denoted by AR. It's the AR of an element and it's the average mass of all the isotopes of an element when compared to 1/12 of a C12 atom. What about molecular mass? Now molecular mass is denoted by MR, and MR of a compound is the AR of all the atoms in its formula added together. Now if we take for example the AR of chlorine, it is 35.5 because it is the average of the isotopes of chlorine 35 and chlorine 37. And if we need to work out the MR of a compound, for example, if we take ammonia, ammonia is NH3. Now nitrogen has AR of 14, so I'll just put that here, NH3. Now AR of nitrogen is equal to 14 and the AR of hydrogen is 1 into 3 because there are 3 of them, so that becomes 3, and since you add these two together, MR becomes 14 plus 3, which is 17. So 17 is the molecular mass of ammonia. Now let's talk about moles. You can define mole as the amount of substance containing 6.022 into 10 to the power 23 particles. Now what is this 6.022 into 10 to the power 23? It's known as Avogadro's constant. The unit of moles is mole. So it's just MOL. And we have the formula. This is the most important formula of this chapter since you will even need to use this formula in other calculations. So number of moles is equal to mass in grams divided by molar mass. Now molar mass is nothing but the MR of the compound or the element. Now this conversion also is important. If you need to convert from moles to mass in grams, you multiply by the MR, and if you are converting from mass in grams to number of moles, you divide by MR. This is the formula itself. Mass upon MR is equal to moles. Now if you need to convert that from number of atoms or molecules to the number of moles, you divide by 6.022 into 10 to the power 23. And if you are converting the other way around from moles to number of atoms or molecules, you multiply by 6.022 into 10 to the power 23. Now here's a sample question to show you how we use the formula of number of moles is equal to mass upon MR. Find the number of moles in 66 grams of CO2. So now this is kind of like the simplest question you can get, where you have the mass, you've been given the element from which you can deduce the MR of the compound. So now let's find the MR first. MR of CO2 equals 12 plus, now oxygen, the AR is 16, so 16 into 2 since there are 2 molecules, so 16 into 2. That will give us the total of 44. Now you don't need to worry about these numbers because they are given in the periodic table already. The relative atomic mass, which is the AR for each element, is given in the periodic table. It's written under the element. Right. So now we have the MR of CO2. Now all we need to do is substitute this in the formula. N, which is number of moles, or you can even write the full thing, number of moles, is equal to mass, which is 66, divided by MR, which is 44. This will give us 1.5 moles. Now Now this is another sample question. Find the mass of MgO when 60 grams of magnesium is burnt in air. So now we have the mass of magnesium, which is 60 grams, and we need to find out the mass of magnesium oxide. We have been told that magnesium has been burnt in air, which means that it's been reacted with oxygen. So our first step is to write a balance symbol equation, which is 2Mg plus O2 gives 2MgO. Then, since it's a tabular method, you'll write mass, MR and number of moles on the side. Mass for magnesium we have been given, it's 60 grams. MR can be taken from the periodic table, it's 24. When you divide the two, you get 2.5 moles. Now, since the ratio of these two big numbers right here is exactly the same, this can be carried forward here. It's going to be the same number of moles. Now, we have the number of moles. We need to find the MR of MgO. So we can use the periodic table again, and oxygen is 16 plus 24, that will give us 40. So that's the MR, and now we have to rearrange the equation for number of moles is equal to mass upon MR. So if we see the equation, it's number of moles is equal to mass upon MR. So if we want to find the mass, you multiply number of moles by the MR, and so we will get 100 grams. And that's the mass of MgO. Reactions stop when one reactant is used up, and we say that other reactants are in excess. In the example question we had seen before, we calculated the mass of magnesium oxide formed. So when we reacted magnesium with oxygen, oxygen was in excess because it is excess in the air. So magnesium becomes the limiting reactant. It is the amount of magnesium that determines how much magnesium oxide is made. So we can define limiting reactant as a reactant that is used up in a reaction. The amount of product formed is directly proportional to the amount of the limiting reactant that is used. So we know how to calculate the theoretical yield of a reaction by calculating the masses in reactions. But if we want to compare the actual yield and the theoretical yield, we use the formula of percentage yield. So the formula for percentage yield goes like this. Percentage yield is equal to the actual yield in grams divided by the theoretical yield in grams multiplied by 100%. So when you get 100% yield, it means that you get all the product and nothing is wasted. Whereas if it is 0% yield, this means that none of the reactants were converted into a product. So no product was made at all. Now let's see a sample question relating to percentage yield. So now we've been given the balance symbol equation. 2ZnO, which is zinc oxide, plus carbon gives zinc plus carbon dioxide. So now we know we have been given that 121.5 grams of ZnO is reduced using excess carbon and produced 78 grams of zinc metal. So we have to calculate the percentage yield. So we go with the table method, write the balance symbol equation. In this question it has been given already. If you get a question where it is written out in words, you need to balance the equation first. Then you find the mass, MR and number of moles. So we have been given the mass of ZnO, which is 121.5. We know the MR of ZnO from the periodic table, and N, number of moles, is 121.5 divided by 81, which is 1.5 moles of ZnO. Now if you see the ratio of ZnO to Zn, 2:2, so 1:1 ratio. This gets carried forward to Zn as well, so it's 1.5 moles. Then we need to find the MR or the AR of Zn, which is 65. And if you rearrange the equation of number of moles is equal to mass upon MR. Number of moles is equal to mass upon MR. We have to find the mass, so we multiply number of moles into MR. So if we multiply 65 into 1.5, we'll get 97.5. If you see the question clearly, it's written 78 grams of Zn has been produced. But this was the theoretical yield based on our calculation. So now, by substituting into the formula of percentage yield. Percentage yield is equal to actual yield divided by theoretical, just writing in short, into 100%. So now we have our actual yield, which is 78 grams. This is what the reaction produced. So 78 divided by the theoretical yield is what we get from the calculation using the mass, number of moles, MR. So that's 97.5. We multiply it by 100%. Put it in the calculator. So 78 divided by 97.5 into 100% will give us 80%. So percentage yield of this reaction is 80. And that will be our final answer. Now if you want to calculate how pure your sample is, we use the formula. Percentage purity is equal to pure yield in grams divided by total impure yield, again in grams, multiplied by 100%. So it works the same way as percentage yield. We can find the percentage composition by mass of a compound using the formula. Percentage composition by mass equals the relative mass of the element or compound divided by the MR of the compound into 100%. Now here's a sample question to show this formula. So we need to find the percentage mass or the percentage composition mass of carbon. So that's the element we need to find, carbon, in 1 molecule of propanol, and we've been given the formula C3H7OH. So the first step is to find the MR of this compound. There's carbon, there's hydrogen, and there's oxygen. AR of carbon from the periodic table, it's 12, for hydrogen it's 1, and for oxygen it is 16. We'll add them up together, so 3 multiplied by 12, since there are 3 carbon molecules, so that's 12 into 3 plus 7 plus 1, 8, and 16, since there's just 1 molecule of oxygen, and that gives us the MR as 60. Now we can substitute in the formula percentage composition by mass. So I'm just writing in short, percentage mass is equal to, now we need to find carbon, and carbon, as we know, it's 12 into 3, which is 36. So we'll write 36 in the numerator, since that's the relative mass of this certain element in the whole molecule of propanol. 36 divided by the MR of the compound, which is propanol, that's 60 into 100%. This will give us percentage of 60. And that's the percentage mass of carbon in 1 molecule of C3H7OH, which is propanol. Next up is empirical formula and molecular formula. Now what's the difference between the two? Empirical formula, it is the smallest whole number ratio of atoms in a compound, whereas molecular formula tells you the actual number of atoms which is there of each element in a single molecule. So now we can calculate the empirical formula in 2 ways, either by mass or by percentage mass, and we'll be seeing questions for the same. Here's a sample question where we are using mass. So calculating the empirical formula by using mass. Iron plus oxygen, that's the reaction. We have been given the mass of iron, which is 44.8 grams, which is reacted with 19.2 grams of oxygen. MR, we know from the periodic table, 56 for Fe and 16 for oxygen. We calculate the number of moles by dividing mass upon MR. Now, we need to make it the simplest whole number ratio. That's the definition of an empirical formula. So this is more like a trial and error method. So you will have to multiply by several numbers. Both numbers which you multiply with must be the same. For example, if you multiply 0.8 by 2, you multiply 1.2 by 2 as well. So if we multiply both these numbers by 5, we'll get a whole number ratio, which is 4:6. But this is not the simplest whole number ratio. So we can cancel this down to 2 and 3. And that is the simplest whole number ratio. So we can write the empirical formula as Fe2O3, since the number 2 is for iron and the number 3 is for oxygen. So you place it after the element. So Fe2O3. And that is our empirical formula. Now here's a sample question using percentage mass or percentage composition by mass. We've been given the percentages of 3 elements: carbon, hydrogen and oxygen. So percentage composition by mass, it just means that 100 grams of the compound contains these percentages of elements. So if you add up these numbers, they'll give you 100%. So you can consider this as 100 grams. Which means that we consider all these 3 percentages as grams as well. So it works the same way as calculating empirical formula using the mass method. For carbon, 26.7 grams. For hydrogen, 2.2 grams. And for oxygen, 71.1 grams. It will work the same way. Carbon, the MR is 12. Hydrogen 1. Oxygen 16. Then we calculate the number of moles. So if we use our calculator, 26.7 divided by 12, we'll get 2.225. For hydrogen, we'll get 2.2. And then for oxygen, we'll get 4.4. So 4.44375. That's a big number. Now we've got all these decimals, but we must divide by the smallest of these 3 numbers. So as we can see, that's 2.2. So we'll divide all of them by 2.2. And we'll get 1 in this case, 1 for hydrogen and 2 for oxygen. So this will give us the empirical formula CH2O2. Since carbon is 1, hydrogen is 1, whereas oxygen is 2. And that is our empirical formula. So as you can see, percentage composition by mass works the same way as the mass method. Only thing is, you need to check from the question if all the percentages are adding to 100%. Because in the paper sometimes they ask you to find the percentage or the mass of an additional element. So you need to subtract. So for example, if there's one more element other than carbon, hydrogen, oxygen. So if you add these 3 and subtract it from 100%, that will be the mass or the percentage of the other element which they've asked in the question. Now if we need to calculate mole molecular formula of something. For example, we've been given the empirical formula as C4H3O2. We've been given the relative molecular mass as 166, and we have been told to work out the molecular formula. As I told you before, the molecular formula tells the actual number of atoms of each element in a compound. So it's not the simplest whole number ratio. So the first step would be to calculate the MR of the empirical formula they have given already. So we multiply 4 into 12 since AR of carbon is 12, plus 3 into 1 plus 16 into 2. And if we add that up, we'll get 83 grams. So that's the MR of this compound. Now we need our compound of the molecular formula has MR of 166. So we'll divide 166 by 83. Sorry for writing the grams. So implies that 166 divided by 83. This will give us 2 empirical units. Which means that we have to multiply our empirical formula by 2 to get the molecular formula. So if we do that, we'll get 4 into 2, which is 8. So the formula will become C8H, 3 into 2, which is 6, and 2 2s are 4, so O4. And that is our molecular formula, C8H6O4. Now let's talk about moles and concentration. Concentration is all about how much of a substance that we have in a solution. We measure the concentration in moles per dm cube, which is also equal to moles per liter. So now this conversion is really important. 1 dm cube, which is also equal to 1 liter, is equal to 1000 centimeter cubes. You need to learn this if you need to convert between dm cube and centimeter cube based on the values they give in the question. Now concentration, there's a formula. Concentration is equal to number of moles divided by volume. You can rearrange it for number of moles is equal to concentration into volume, and if you need to find volume, using number of moles divided by concentration. So if concentration is in mole per dm cube, your number of moles is obviously in moles and your volume will be in dm cube. So if you've been given volume in centimeter cube, you have to use this conversion. 1 dm cube is equal to 1000 centimeter cube, and you have to divide your volume by 1000 then to get it in dm cube. Now when you calculate concentration or volume or those kind of questions, this will again come in handy to convert from moles to mass in grams, or to convert from the number of atoms or molecules to moles. So just to refresh, moles multiplied by the MR will give us the mass. So this is basically the formula, number of moles is equal to the mass upon MR. You need to remember the other side of it, where you have to convert between moles and the number of atoms or molecules. So if you want to convert from the number of atoms or molecules to moles, you divide by Avogadro's constant. And if you have to convert the other way around, from moles to the number of atoms or molecules, you multiply by 6.022 into 10 to the power 23. When you need to calculate concentration, usually in the exam paper, they give you titration questions. So titrations are experiments which allow you to find the volumes of two solutions that are needed to react together completely. For example, you can use the results of a titration experiment to find the concentration of an alkali when you know the volume and concentration of the acid which was reacted with it. So basically the logic behind this is that if you know the concentration of one of these solutions, you can use the volumes which is taken from the titration experiment along with the equation, the balance symbol equation for the reaction, to find the concentration of the other solutions. So now we'll see an example about a concentration question. Now here's a sample question where we are calculating concentration and volume and number of moles. We are using that formula. So the question goes like this: calculate the volume of aqueous NaOH of concentration 0.20 mole per dm cube, which would be required to neutralize exactly 25 centimeter cube of dilute H2SO4 of concentration 0.25 mole per dm cube, and we've been given the balance symbol equation. So now first thing is identify the values which you have been given along with the compound. So now we have NaOH, we have to find the volume of NaOH, we have the concentration of NaOH, we have the volume and concentration of H2SO4. Second thing to remember is that volume of H2SO4 has been given in 25 centimeter cube, and we know that we need to calculate it in dm cube since all the other values are in mole per dm cube. So immediately just use the conversion. 1 dm cube is equal to 1000 centimeter cube and divide 25 by 1000, so you won't get an error in the middle of your calculation. Again, we use table method. Write out the balance symbol equation. If they have not given it, you need to balance the equation out first. Then since we have the concentration, volume and number of moles, we'll write that on the side and put in the values that we have already. So we have 3 values and I have put 25 divided by 1000 dm cube here. So first step is, since we have both these values, we can calculate number of moles of H2SO4, which is 6.25 into 10 to the power minus 3. So this is the number of moles of H2SO4. Now if you see the ratio, 2:1. So we multiply this by 2, which will give us 0.0125 mole. So now we have the moles, we have the concentration. We make the formula triangle or write out the formula. Number of moles is equal to concentration into volume. And we have the concentration, we have number of moles. So we need to find the volume, divide number of moles by concentration. So 0.0125 mole divided by 0.20 will give us 0.0625. dm cube of NaOH, and that is the volume of NaOH that we will get. And now for the last topic of this chapter, which is calculating gas volumes. So Avogadro's law also states that 1 mole of any gas occupies 24 dm cube. So the space which 1 mole of a gas takes up is called the molar gas volume. And you need to know this formula. Volume in dm cube is equal to the number of moles of gas multiplied by 24. And remember that 24 is in dm cube. So if you need to calculate the number of moles of any gas at RTP, which is basically room temperature and pressure, you just substitute it into this formula. Number of moles is equal to volume divided by 24. Just make sure that the volume is in dm cube. So if, for example, you've been given in centimeter cube, divided by 1000, based on this conversion of 1 dm cube is equal to 1000 centimeter cube, and then divided by 24 dm cube to get the number of moles of that certain gas at room temperature and